morning, everyone. Good morning. It is my pleasure to welcome all of you to Cambridge and to Harvard. It's a little cool, but it's still sunny outside, and we did send a message: bring sweaters, bring jackets, bring scarves. So I'm sure you came well prepared. Let me introduce my colleague, Professor Jim Stock, who is the Vice Provost for Climate and Sustainability, and also the Faculty Director of the Salata Institute for Climate and Sustainability. And he, with his vision, decided that of the 5 inaugural grants the Institute gave, Africa should be one. So we are grateful to him for this opportunity to come together to reflect on Gulf of Guinea and climate adaptation and all the important things. So please join me in welcoming my colleague.
Thank you, Emmanuel, and it's great to have everybody here. I hope that you are, I would imagine the jet lag is settling in for some people, so good luck. I'm sure that the program will do its best to keep everybody going. It looks like a fascinating program. As Emmanuel said, I'm really excited to be able to support this group as one of our first 5 research clusters, climate research clusters. We focus here at the Salata Institute. So the Salata Institute, which I'm a director of, sits at the center of the university, and it reports to the provost. And I'm also the vice provost for climate sustainability. At the Salata Institute, our goal is to drive research and positive progress towards dealing with climate challenges. Some of those are on the side of reducing emissions or mitigation. Some of those are on the sides of adaptation. And certainly the challenges faced in Africa in both counts, but especially in adaptation, are particularly striking. So it's especially important, and I'm very pleased to be able to for us to have the opportunity to support this particular project working on sea level rise in Africa. Emmanuel and his colleagues have assembled a great team working here. I see Jerry, and I thought I saw Rob. I see Rob? Yeah. Okay, there we go, okay, with sunlight in my eyes. And I'm really excited to be able to, we're excited to be able to support that, and I hope that this collaboration between Harvard and the universities in the Gulf of Guinea and all of you who are such serious participants in this incredibly important problem is going to be a prolific one and a successful one and an impactful one. So with that, thank you very much, Emmanuel, and I hope you have a great conference.
So I will call on Jerry. Will you introduce yourself?
Sure. I'll be ready to go.
Yeah.
Okay, hello everyone. Sonke is well known to us. He was here 1 year ago in our last November meeting. When we discussed the keynote, he was the natural choice for that. I think it's fair to say at Harvard, we have focused on climate physics. We have experts in all sorts of aspects of climate science. But what distinguishes Sonke and why he is the world's leading data analyst related to sea level is that he brings that physics together in a really elegant statistical or probabilistic framework, and he's doing state-of-the-art work on things like hurricane, extreme climate events, etc. He's also advising one of the postdocs, Rebecca, on a project, Pan-African project, to see that an application of what he's going to be talking about today on understanding and quantifying the level of sea level rise over the last 50 years in Africa, but not only that, the various contributions to that sea level rise. And it's really only Sonke, it is Sonke leading this work internationally. So when Emmanuel suggested a keynote, it was an obvious, easy decision, and we appreciate that Sonke's fit us into a very tight schedule. He leaves tonight for Washington, but will give us an overview of these new methods And Rebecca will speak later to the application of these methods to the Gulf of Guinea and to Africa at large. Sonke, welcome.
Thank you, Jerry. Thank you, Emmanuel, for the invitation. It's always a pleasure being here, and has been great to collaborate with all of you on this project. Today I will talk a little bit about, as Jerry already said, unraveling coastal sea level changes since 1900. This work has been done with a number of different collaborators, including Jerry. They are all mentioned below, and a couple of different projects funded by NASA, NSF, and the National Academy of Sciences. Coasts have always been threatened by extreme sea levels, triggering flooding, which of course leads to loss of life, economic and ecological damage, and others. At the same time, 1/10 of the Earth population lives in areas below 10 meters, and indeed 2/3 of the world's largest cities is in that zone. And more importantly, people are still increasingly moving into these cities, making them more and more vulnerable, right? At the same time, we have seen that climate change due to sea level rise has been exacerbating coastal flooding and the associated impacts. For instance, there was a study a couple of years ago that estimated that about $8.1 billion of Sandy's damage was due to climate-induced sea level rise over the 20th century. So, and this all just illustrates that it is extremely important that we understand sea level rise and its causes and its drivers to become more resilient. And in my talk today, I want to talk about 3 different sub-projects that are interrelated. In the first part of the talk, I want to talk about a probabilistic spatial and temporal sea level reconstruction since 1900 that we published earlier this summer, which provides sea level information at any place on Earth. Then in the second part, I want to talk about an application of how we can use that information of climatic sea level and compare it to individual measurements along the coast that may have additional processes such as vertical land motion in it, and how we can learn from, like, constraining the climatic information about these very local processes. And then in the last part, I want to introduce a new framework that we developed very recently to not only disentangle the individual processes contributing to sea level change, but also the anthropogenic and natural drivers, which brings us into the detection and attribution realm. So let me start with the first topic, and to give you all a brief introduction of where we are. We nowadays have a very modern remote sensing observation system that allows us to very accurately track global mean sea level rise and its individual contribution since about 20 years. We have what we call the satellite altimetry record, which measures sea level from space relative to the Earth's center of mass with a complete global coverage. That's the black line that we see in the lower left of this graph. And it shows that global mean sea level has been rising by about 3.4 millimeters per year since 1993. At the same time, we also have a satellite system called GRACE, which measures mass fluctuations on Earth. So it gives us estimates of what we call the barostatic mass contribution to sea level rise. It comprises glacier melting, ice sheet melting, and any water that was previously stored terrestrially, like land water, for instance in aquifers or in the hydrological cycle. And then we have, that's the blue line in that lower left graph. And then we have Argo floats, which measure temperature and salinity and pressure in the oceans. And they allow us to estimate what we call the thermal or steric expansion of the ocean. If the ocean warms, it needs more space. So water molecules need more space. It expands and leads to sea level rise. That is the red curve here for the global average. And if you add both of them together, the barostatic mass and the thermal expansion part, then we get the purple line, and you see it nearly perfectly matches the independent satellite observations of global mean sea level, which shows that we have a very good understanding of global mean sea level over that period where we have these remote sensing observations. However, if we go towards local levels, and in particular before 2004, sea level is way less well understood because we have additional processes happening in the ocean. For instance, we have a component that we call stereodynamic sea level change. Thermal expansion or salinity changes are not homogeneously around the globe. And we have ocean circulation system and winds carrying water masses, heat and salt from one place of the ocean to another, and that leads to regionally varying rates of sea level rise. We have pressure systems over the ocean that change the sea surface height, and that's what Jerry has made a career of, is we have the ice melt fingerprints. So if an ice sheet melts, of course, you add mass into the ocean, but at the same time, you change the gravity field of the Earth, leading to a migration of water away from the ice sheets. And at the same time, the ground beneath pops up. So what we see is a relative sea level fall that accompanies barostatic mass changes into the ocean. And all of these processes lead to very unique geometries in regional sea level around the globe, and that's visible in the map in the lower left. That's the satellite record. The global mean is removed, so it's just the spatial variability over the last roughly 30 years. Blue areas mean below global mean sea level rates, and red areas mean above global mean sea level rates. And you see that there's variability in the order of plus minus 6 millimeters per year, probably, which results from all these processes. An additional problem is that when we move beyond like 1993 or 1992, when satellite altimetry became available, then the only information that we are left with is in terms of tide gauges, which are basically wooden poles that measure sea level relative to the Earth on which they are grounded at the coast. So they have been implemented in the 19th century or later, first for the belongings of shipping, but they carry very important scientific information on relative sea level, but only along the coast, and they are very sparse. So you see now in that same map, these little circles, these are the trends as observed by tide gauges. And you can imagine that it's very difficult to estimate that entire surface from that sparse data. An additional point here is if you look at these individual circles, you see while they match in some regions, there are a lot of regions where the color is either way darker than from surrounding satellite altimetry or even opposite. And the reason for that is that tide gauges track sea level relative to the Earth, meaning that they also track any vertical motion of the land on which they are grounded. And that can be due to processes such as spatial isostatic adjustment. That's related to the ice melt from the last ice age. The Earth is still adjusting to that. So you see uplift and subsidence in some regions related to that. That's a natural process. But then in particular over the last century, there have been anthropogenic influences such as groundwater or generally fluid withdrawals due to oil and gas coming on top of that, leading to subsidence in many coastal regions. And that becomes clear that it's very complicated to actually estimate the entire surface and the global mean from that sparse data set. The way how we handle that is we use a framework based on a Kalman smoother, which is a probabilistic state estimate that uses both observations and models to predict a dynamical system. And it's particularly well suited here because the observations are so sparse. The framework has actually been developed in Jerry's group by his postdoc at that time, now more than 10 years ago, Carling Hay, with a prime paper that has been published in 2015 in Nature. And we have taken that framework and adjusted it in a way that we integrated prior information on the temporal and spatial development of, for instance, different ice sheet and glacier contributions that have become available in the meantime. We have implemented prior knowledge on glacial isostatic adjustment. We have integrated the inverse barometer effect, that's the sea level pressure response of the ocean. And we also have integrated a reconstruction of what we call the aerodynamic component due to expansion and ocean circulation changes. And that comes into the Kalman smoother. And all these fields are constrained by the available tide gauge observations. So what we get at the end is an estimate of global mean sea level plus the spatial fields from these processes. And we are not only able to actually estimate the entire sea surface height over the oceans, but also all the individual processes with the different uncertainties. And with that, I want to walk into the actual, through the actual results. This is the first validation that we did with satellite altimetry observations. In the upper left of the figure, you can see a correlation map between our reconstruction and satellite altimetry. Dark blue means a correlation of 1, so nearly perfect agreement, while more light or red areas would mean no correlation. And you see it's almost everywhere dark blue. On average, we have a correlation of 0.87 over the global oceans. When we average regionally, it becomes larger, 0.92 on average. And for the global mean, we have a correlation of 0.96. In the different subplots, you also see the time series of global and basin scale average sea level. In blue, the reconstruction, and black, satellite altimetry, and then the different colored curves are the individual contributions. The most important part here is the agreement with satellite altimetry. You see it matches it's almost identical. And we also looked at the spatial trend pattern from the reconstruction and satellite altimetry and the acceleration pattern. I don't show that here, but I can report the results. And you can see that in the publication. The spatial correlation is 0.97, and we track the trends with an error of 0.4 millimeters per year, which is very, very accurate for sea level reconstruction. But of course, satellite altimetry goes as in terms of the spatial variability into the reconstruction process, or it informs the reconstruction, so it's not a 100% independent validation here. So that's why we actually looked into temperature and salinity data. In the whole framework, there's no temperature and salinity data going in. So this is a completely independent validation. So we look into the aerodynamic component that we reconstruct within that process. Our estimates are now shown in yellow, and then we compare that to independent estimates of spheric sea level change in the oceans from different observational estimates, which are shown in the different colors. Most of them are available only since the 1950s. There's one estimate which is solely based on sea surface temperature that goes further back in time, but it comes with a lot of uncertainty. The general picture is here that the agreement is fairly well between all those products, in particular given the fact that none of that information made it into the reconstruction, and temperature and salinity observations itself are very uncertain as well. It also becomes visible when looking into the regional basin scale time series on the right side. You see that the correlations are very high, usually between 0.57 and 0.87, and the trends are also well reconstructed. So that gives us really confidence that our reconstruction does a reasonable job here. So what does the reconstruction really offer? To give you an example what we now can do, this is the Boston tide gauge here in gray in the time series since the early 20th century, and then in blue you can see the reconstruction with its uncertainties. but we can now also break down the reconstruction into the individual contributing processes of stereodynamic sea level change, ice melt, the gravitational, rotational, deformational fingerprints, the sea level pressure contribution, and the glacial isostatic adjustment. So, and that has not been possible before. An additional point that I want to emphasize, that information is not only available at individual tide gauges, but everywhere along the coastline. So we can really resolve the entire coastline. This is just for illustration here, the US East Coast. And Rebecca actually will present some results for Africa, where almost no tide gauge information is available this afternoon. So we also try to validate the reconstruction at tide gauges. And we did that first with a reconstruction that only incorporates vertical land motion due to glacial isostatic adjustment. Keep in mind, the tide gauges also track other vertical land motion, but that is not included in the reconstruction because there's no data available on that for the 20th century. So we did that for 90 tide gauges, which are shown in the map, and the map shows the differences between the linear trends estimated from the tide gauge and the nearby reconstruction. So you see some different colors. And the statistics of it are that the differences are in the order of 0.27 millimeters per year with a standard error of 1.67 millimeters per year, which is at the upper end of what is possible with sea level reconstructions. And it's an improvement to previous attempts. But there's still a relatively large error in reconstructing the trend. So the question is, why is that the case? And I just mentioned what we don't include in the reconstruction process is local vertical land motion other than glacial isostatic adjustment, because it's not available over the 20th century. What we can do, we have estimates from the Global Navigation Satellite System, GNSS, but they only are available over the last couple of years. So we can extract information about subsidence or vertical land motion in general from those, replace that information with a glacial isostatic adjustment, and then do the same comparison again. And if we do that, we actually see that the differences go down to minus 0.13 millimeters per year with a standard error of only 1 millimeter per year, meaning a significant reduction in the error, which indicates that a lot of the remaining differences between the reconstruction and tide gauges are actually due to vertical land motion. And it is not that GNSS is the only true measurement that we, or the ground truth. It's the best measurement that we have, but it comes with a lot of uncertainty as well. And that actually gave us the motivation to look deeper into that process. So we had the idea, okay, we know now that a lot of the differences that we observe between tide gauges and the reconstruction are due to vertical land motion. Maybe we can use these differences to infer vertical land motion over the entire period over which the reconstruction and tide gauges are available. And again, the problem is GNSS is only available usually since the early 2000s or later. So if there is nonlinearity in the vertical land motion, for instance, due to fluid withdrawals or something, that is not captured by any measurement system that we have in place. So if you use the differences between the reconstruction and tide gauges, we might get information that was previously unavailable. So, and that's the idea that I want to introduce next. So to give you again, like a general idea how we track vertical land motion nowadays, it's usually available at a few tide gauges worldwide with a GPS antenna at a tide gauge, but actually very few tide gauges have that. Very often these GPS measurements or GNSS measurements are from the surroundings, like a couple of kilometers away, and you have a lot of spatial variability in vertical land motion, which makes the comparison very hard. The alternative way of estimating vertical land motion at tide gauges is using the difference between nearby satellite altimetry and the tide gauge, because satellite altimetry measures sea surface height relative to the Earth's center of mass, and the tide gauge measures it relative to the Earth. So if both measure the same ocean signal, the difference should generally be due to vertical land motion, right? And our idea here is to just replace satellite altimetry by our reconstruction because it goes way farther back in time to 1900. So we did that, and we did first a validation check with available GNSS measurements. So the upper map, the shading, shows the vertical land motion from a state-of-the-art GNSS product from Nevada. And the circles show estimates from the difference between our reconstruction and a tide gauge at every location that we have available. Just visually looking at the map, you see that the colors match very well, but we wanted to do a more straightforward comparison, so you also see these different scatter plots at the bottom of this figure. In the lower left, you see the comparison between the tide gauge the reconstruction and tide gauges, and the altimetry minus tide gauge, which is one of the standard techniques. We have 430 locations worldwide where we can do that comparison. The coefficient of determination, the R-square, is 0.99, and the standard error is only 0.4 millimeters per year. If we do the comparison with GNSS in the middle panel, there's one product which comes from France, which is only at tide gauge measurements, or within 1 kilometer around the tide gauge. We only have 46 stations worldwide in our data set that fulfill that. The coefficient of determination is still 0.85, and we get a standard error of 1 millimeter per year, which is very decent for that technique. We also have a different GNSS data set, the one that is spatially shown in the upper map that comes from Nevada. It's an interpolated product, but it has way more locations available. If we use that, we have 175 locations. We get an R-square of 0.85, and again, a standard error of about 1 millimeters per year, which really reinforces the idea, yes, the differences between our reconstruction and the tide gauges are actually measuring local processes such as vertical land motion or any other datum issues. So in the next step, we said, okay, let's look into a couple of examples and see whether we can actually see nonlinearities over the 20th century. So, and I'm just walking you through a couple of examples now around the world. Let's start with the lower left. That's Bangkok in Thailand. In the little insets, you see in dark blue, that's the tide gauge record that has been observed. And then in cyan, you see the nearby sea level reconstruction. While it decreased fairly well into the 1960s, after the 1960s, there's a sharp increase in the tide gauge record that is not reproduced by the sea level reconstruction. So we take the differences between these two, and they are now shown as the gray error bars in the large plot. And you see again, it's relatively flat in the first 20 years until the 1960s, then that sharp decrease, and then it flattens out a little bit again since the 1990s. So the thing is, we know that Bangkok had a tremendous increase in population, and they extracted a lot of groundwater over the 20th century. So I digitized data from groundwater extraction in Bangkok, and these are the yellow dots, and you see it matches nearly perfectly these sea level differences, which again indicates that these sea level differences are indeed resolving nonlinear subsidence in Bangkok. And we said, okay, maybe we are lucky. It's just a lucky punch that we did it in Bangkok. So we went to Venice, did the same thing. In Venice, actually, it's not a digitized groundwater withdrawal estimate. It's actually coming from levelings from GNSS data and INSA information, so actual measurements, shown again in yellow, and you see it's almost a one-on-one match. So it really resolved the nonlinear subsidence that happened in Venice. The fact that it leveled off again is, in both cases, that they actually did something about groundwater withdrawals, and that's what slowed it down afterwards.
Why did they do it? Were they aware of the fact that they were worsening the effect by pumping groundwater?
Yes. Yes. And there are a couple of examples, like Tokyo, for instance, had the same thing. They solved it basically in the 1980s, I think. And then an additional point is we can also have nonlinearities in subsidence due to earthquakes, right? So I picked an example from Pago Pago in the Pacific Ocean. Again, the sea level differences show a generally decreasing trend, which indicates subsidence. But then after 2009, there's that sharp decrease. So I looked into GNSS measurements, and it showed exactly the same thing again. And then I did some research on that and found that there was an earthquake, the Samoa earthquake from 2009. So what we see here is post-seismic deformation that is resolved by the differences. So we can also resolve earthquakes. And that becomes even clearer when going to Japan. Here I show a couple of records along the east coast of Japan. And then the colored lines are just showing a smooth version of the sea level differences. And then there are two records from GNSS available from the region that are nearby the tide gauge locations, which are again shown on yellow. And you see the Tohoku earthquake from 2011 led to a vertical displacement of up to 1 meter, which is completely resolved by the sea level differences. And all those matches exactly, again, the GNSS observations, which again shows, yes, it's not only that we can now reconstruct sea level anywhere around the globe, we can resolve the different processes, but we can also like track that back and like compare that estimate to the actual measurements and make sense of processes that were previously lost in the climatic noise, right? So it all seems to make sense now. And that information, of course, can be used to actually implement that knowledge later into sea level projections, because those processes are not well determined by any measurements. So this data set, I think, can be the baseline to work towards like seismic-induced nonlinear subsidence or due to groundwater withdrawals for sea level projections as well. So in the last part now, after showing that we have now a decent understanding of sea level rise anywhere around the globe, including the different contributing processes, I want to move into the last chapter. We just developed within a NASA project a detection and attribution framework for sea level, where we try to disentangle anthropogenic and natural drivers of sea level change, and then also look into extreme events, so extreme storm surges. To give you an idea what that means, like in the upper right, you see a plot just schematically. The black line represents an observations. And then we can use climate models, which offer the opportunity to model the historical climate using similar parameterizations as for the future. And the big question is here, do they reproduce the actual observations? And they are represented here by the yellow or orange shading. So this is an ensemble of climate models. It's important to mention climate models are meant to reproduce multi-decadal climate variations, but they all start from their own initial conditions, meaning that they will not give you an exact match with observations in terms of individual peaks that are caused by things like ENSO, for instance, natural climate variability, but they are meant to match your observational record on average over 30 years. So that's why you use a large ensemble of climate model simulations, and it should produce the same low frequency trend. And if that is indeed the case, then you can use single forcing runs from the same climate models where they keep individual forcing factors such as greenhouse gases, aerosols, solar forcing, or volcanoes constant, and then you can look through the different experiments and actually find the forcing factor that caused the increase or decrease depending on the variable that you're interested in. But the main thing here that we need to clarify at the beginning is, are the climate models actually able to reproduce the observations or not. And that's the first thing that I want to do on the next slides. Our detection and attribution framework for sea level is based on a global assessment from Slangen and colleagues from 2016. They implemented that just for global average sea level, but they didn't do a regionalization. So what is new here is the regionalization. So we use the fingerprints of ice melt and terrestrial water storage to regionalize all the information. We used ocean dynamics from climate models to get the stereodynamic component right. We included inverse barometer contributions. And we also corrected the observational record for terrestrial water storage variations, which are not resolved by climate models. And we also added information on vertical land motion, which again is not modeled by any climate models. An important note here is we are interested primarily in extreme sea level, so extreme events, and the contribution of climate-induced sea level rise. So we have our base assumption here that the extremes, the trends in the extremes are primarily induced by sea level rise. And that is underpinned by the current state of the art of research. We have investigated over decades trends in extreme sea level events along the coastlines. And in most of the cases, the trends in the extremes are primarily induced by the underlying mean sea level rise. So now let's look into the comparison between climate models and the observations. This is shown here now in these three different subplots. In the upper left, you see the global average sea level from the reconstruction, again in blue. And then in black, you can see the ensemble of climate model simulations. And you see it's nearly a perfect match. So that was already known from the publication in 2016 from Amy Slangen. An important note here is that there is a correction that goes into glacier melting and ice sheet melting in the early 20th century that is not reproduced by climate models. The reasoning here was that the observations have trends in the early 20th century which are not reproduced by climate models. And it has been the assumption that that is a natural event, a natural variability that is not picked up by climate models. So here we follow that assumption and saying that it all moves into the natural contribution of sea level rise in the early 20th century, but that is a very conservative estimate. In reality, it's very likely that there's a way bigger anthropogenic contribution in the first part of the 20th century. But this is like a first step towards actually getting an estimate of what is our contribution as humans that can then serve also for climate litigations, for instance, right? So if we look at that, the match is very good globally. I also plotted here the Gulf of Guinea for comparison. It's also a very good match. And then in the lower part, you see the linear trends with the white shading always for the entire 20th century, 1900 to 2005. That's where the climate model simulations are available. And then the gray shading represents the trend for the period 1970 to 2005. Again, blue are the observations, and black is the ensemble of climate model simulations. Main message here is that the spatial pattern of sea level change is very well reproduced by climate models, which gives us confidence that we can proceed with the detection and attribution framework towards a local level as well. The green and red always represent the contributions of natural and anthropogenic contributions, and the yellow is terrestrial water storage, for instance, due to the building of dams and groundwater pumping. That is kept separately because it's in the observations, but it's not modeled by the climate models. So if you look at the long period since 1900, natural forcing is the dominant cause, again, with the underlying base assumption that the early 20th century ice melt was primarily a natural event. But then since the 1970s, it totally flips. So it's almost entirely anthropogenic forcing that has induced the sea level acceleration in the second part of the 20th century. So that's basin scale, but we are interested in individual extreme events at individual locations, so we want to move to a really local level. So we looked into actual tide gauge observations. Again, this is a mean sea level comparison, and this plot in the middle shows the linear trends over the entire available period of tide gauges, in blue, and then in black the historical experiments from the climate models. The correlation between these trends is close to 1, and the standard error is again in the order of 0.4 millimeters per year, which really indicates that we are able to reproduce that. An important note here is to resolve that locally, we need to include that vertical land motion information that I presented before, so that makes it here into the climate simulations. That is part of that. You can also see individual examples for individual tide gauges on the right side, like Grand Isle in Louisiana, San Francisco, or Manila below. And again, you see the black lines align very well with the blue observations, indicating that we can do local attribution of sea level rise. And when we look at the actual forcings, we also see, again, the same thing as globally, that over the first half, it's very uncertain, but then since the 1950s, 1960s, it's really anthropogenic forcing that dominates. Oh, I'm sorry. What happened here? So it's really anthropogenic forcing that dominates the most recent decades. But again, we are interested into extreme events, like individual storm surge events. So for that, we selected hourly tide gauge records to extract actual extreme events. There is another database that we need, the so-called GESLA database. That data was available at 117 out of 149 tide gauges that we used before. And the data needed to span at least 15 years. So then we went into each individual record. We first detrended it by annual mean sea level. This is now shown for Grand Isle in Louisiana. Exemplarily, the blue line represents the hourly observations, and then we actually select extremes based on a peak over threshold technique using the 99.7th percentile. These are the red crosses, and we make sure that we are picking independent estimates, events, by declustering the events by 7 days, making sure that these are really independent search events. Then we fit a generalized Pareto distribution to the extreme sea level data set to estimate the return levels and return periods. And we do that for the full available record, but also in time slices to see whether the main parameters of the distribution changed over time. And indeed, at most locations, or at all locations, we see an increase in the GPD threshold. And we made a comparison at those sites. At most sites, it's mainly a function of mean sea level. And that also means, again, that we can use our detection and attribution framework on mean sea level, apply it to these extremes, and then estimate the anthropogenic and natural contributions to it. And this is now exemplarily shown again for the tide gauge of Grand Isle. In the upper right, you can see the return periods and return levels. So the statistical fit to estimate, let's say, a once in 100-year event and the associated return level. The blue line in this graph is actually the estimate from 1900. The thing is, we estimate that curve first from the observations, but we know that the climate model simulations are able to reproduce it. So if you use the climate model simulations, which go back to 1900, we can now model the development of that entire curve over time from 1900 to 2005. And you see the shading from blue to red. This shows just like the different years and the change with mean sea level over the 20th century. So you see that what was a once in 100-year event in 1900 is now shifted upwards due to the underlying sea level rise, leading to higher return levels and shortening the return periods. So what was in this case, for Brent Isle, what was a once in 100-year event in 1900, you can see that in panel B, has become over time now almost an event which happens once every 50 years, okay? And at the same time, the return level increases. And you see that in panel C. But we can also go now into the individual contributions from natural forcing, anthropogenic forcing, and vertical land motion. In this particular case, in Louisiana, we have a big subsidence problem induced by different processes. It's a delta, but there has also been a lot of oil and gas production that has accelerated subsidence in the region. So you see the biggest factor here is really subsidence due to oil and gas withdrawals in this particular case.
Sonke, return level means amplitude of the extreme event?
Yes, that's the peak of a storm surge event, yes, of an extreme event, yeah. Thanks, good question. So we did that, of course, for any location now worldwide. And what is shown in this map is the return level of what was a once in 100-year event in 1900 in 2006, in the last year of the simulation. So if that is dark red, it means that what was a once in 100-year event in 1900, has become an event that occurs now more often than every 5 years. So you see a lot of red in this map, and you see a few blue patches. The blue patches are usually what Jerry model is most interested in. That's glacial isostatic adjustment. It's uplift of the land. So there are a couple of safe places in like Scandinavia and North America. But most of the coastal regions have seen an increase in extreme events and a shortening. So the events happen more often. And that, of course, increases the pressure on the coast. You can also now go into the histogram, which is shown below. On the left side, it shows the entire historical forcing from climate models. And it shows the same information as in the map. But you can see how many gauges actually see, for instance, what was a once in 100-year event in 1900 occurs now more often every 10 years. That's more than 40. So you see the whole spread. There are a lot of tight gauges. On average, we have seen a shortening of the return periods from once in 100 years to once in 14 years. And then on the right side, we can see the individual forcing factors contributing to it. And anthropogenic forcing has shortened the return periods from once in 100 years to once in 34 years over the 20th century already. So it's the most important driving factor of extreme sea levels along the coast. Natural forcing have the same effect. Again, take it with caution here, because the early 20th century is based on that assumption that it's all based on natural variability, which is unlikely to be the case. Subsidence induces, so the purple lines induces the most extreme cases, but it's only individual locations. So on average, it is less important than natural and anthropogenic forcings over all tide gauges, so it has shortened it to 72 years. And terrestrial water storage has usually had an opposite effect, but very minor. So what was a once in 100-year event became once every 109 years event. So and that brings me to the end. So wrapping up a little bit, so we introduced a new Kalman-Smoother-based sea level reconstruction that includes prior information on observed ice melt, fingerprints, glacial isostatic adjustment, inverse barometer effects, and UFs representing stereodynamic variability. which allows us for the first time to do an improved assessment of the 20th century sea level budget, not only globally, but also locally, where it matters the most. So this allows us for sea level evaluation and assessments, even in data-sparse regions such as Africa, right? And Rebecca will tell us more about later today. We also can use that information now at individual tide gauge locations for the detection of unmodeled near-coastal processes such as nonlinear vertical land motion due to earthquakes or fluid withdrawals, a process that is not included in any sea level projections yet. And then finally, I introduced a new detection and attribution framework, which allows us for the assessment of sea level rise-induced changes in return levels and periods due to natural and anthropogenic forcings, vertical land motion, and terrestrial water storage. And the main message here is what has been a once in a 100-year event in 1900 has on average already become a once in every 14 years event in 2006. And the most extreme case actually was on the Philippines, a location where the once in a 100-year event from 1900 now occurs already more often than every 50 days. So just to give you an idea, the sea level tool, the reconstruction is fully open access. It's available via Zenodo. And I also want to advertise this new earth.gov website, which is the first collaborative website from major US agencies. Yes, it's surprising they can actually work together, NASA and NOAA, all in one boat on one website. And World Bank is included here, and this gives, it has a sea level assessment tool, a sea level explorer. You can go to any location worldwide, get information about sea level based on the observations, based on the sea level reconstruction, and see how the sea level hazard has changed over time. It also includes estimates of extreme events for all global EECs. So look at the website. It's a really valuable tool to get an idea how your region looks like, and the data behind that is all freely available. So you can actually use it to determine the hazard in your specific region. And with that, I want to thank you for the attention and take any questions.
You will moderate questions?
Yes, I will indeed. Do you have a question?
Thank you, Sonke. That sparse Gulf of Guinea, I would say, only one gauge between Accra, Senegal, and Yaoundé, Cameroon. Only one gauge in Ghana. And you do know that we've been told that for us in Lagos, it is the ninth sinking city by reason of groundwater extraction. We do know that for Nigeria, the Niger Delta is one of the fast sinking areas because of hydrocarbon, and they're still removing it. My question is there any preliminary window? No, that's why we're here. Any preliminary window that we can use just to look at what the problem will be, so that we'll be able to be thinking what the solution we can give. Any window for us in Gulf of Guinea, just preliminary window, because we've not gotten everything we want right now.
Yeah.
We know the crisis on ground. We know there are about 4 land tremors in Nigeria in the last 1 year, which should not be so.
Yeah.
And they trace it to the extraction is there, the issue of Cameroon, what's it called? The tectonic plate is there, 4 in the last 1 year. And we're wondering, nothing's on ground. Any preliminary window we can just look, can be time that Jerry and the team in science will come with detail for us to start thinking we have a problem, and this is what we can do. We don't want to wait until the problem comes. Is there any preliminary window? Thank you.
Yeah, I hope I'm understanding the question right, but I think what is needed is first, like, a thorough assessment of the present day hazard, and then how that evolves in the future. So the problem again is that there are no tide gauges, or only very few tide gauges, and the tide gauges that are available have massive problems. So they go up and down, and that is something that Rebecca will show later today. But again, these spatial reconstructions, including the individual storm surges, now allow, at least for a good estimate of the hazard over the last 30, 40 years, even if you don't have actual observations. So you can check those at the surrounding places, and then use them as an estimate of the present day hazard, and then combine it with available sea level projections. The projections are available. They just need to connect it to that observational data. So my suggestion would be, or my advice would be, to look into these data sets, determine the present day hazard, which is already like a big undertaking in general, and then couple that with available projections to get an idea of the hazard and do all the associated things. Like that can be easily coupled with the work done by Peter Hybers to think about compound flooding. I remember, again, from the last year, the main problem is not necessarily a storm surge, it's inland flooding that produces a lot of problems in the region. So I think that would be a really nice way forward to merge these different data sets and improve the situation of the hazard assessment.
In some ways, that's Rebecca's role here will be to take all of this and apply it to the Gulf of Guinea. Right? We somehow in our original discussions we thought it was pointless. There's no data there. There's a couple of tide gauges, but that combined with the satellite altimetry and these other observational data sets like GRACE really gives us an opportunity, even along the Gulf of Guinea, to, as Rebecca will show later, say, here's what's been happening in the last 50, 100 years, here's why it was happening, eventually, here's how often these storm surges are going to happen, because the ultimate goal in the project was a vulnerability index for that coast, and all of these things are necessary to assess that. Right? Robert?
Thanks for a wonderful presentation. If I were the mayor of a coastal city, I'd be most interested in your modeling of shortened return periods for extreme events. And the link to climate change is immediately plausible, but why link it to sea level rise? Would ocean warming be a more direct link for understanding the probability of extreme storms?
It is a way more complicated factor. So the thing is, the observations of storm surges or storms are way more sparse than the mean sea level rise information that we have. And the knowledge about those is way less. But there is very limited evidence from the global coastlines that there are significant trends in storms, or the trends are way smaller than sea level rise itself. And the projections are also still like in a range, at least what the climate models, the coarse climate models give, that is not the biggest factor. So I agree, yes, it is an important factor, we need to look at it, but this is the first step. So the next step would be to integrate also changes in storm periods. So we assume that storm surge climate has been stationary over that time, which is backed up at many locations, but there may be individual locations where we actually also see trends in storms. So, yeah.
Question for all of you. Totally the outsider here. I'm a clinician. I don't study sea level rise. But this comment about paucity of gauges is also true with weather station data, right? We sort of face this. The U.S. is saturated, and the global south, you just don't have enough. And then when you try to downscale these models, you find that it does not account for the heterogeneity of the microenvironments of the poor, especially. Millions of people with very different experiences. So a very naive question. How expensive is it to deploy tons of more gauges? Why is, of course this is important, but why also not more gauges? Why do we seem to have sort of frozen in time since the Brits left? The Commonwealth has the gauges that the Raj had in India. Is it prohibitively expensive? Is it maintenance? Is it personnel capacity? Why has that been abandoned?
I would say that it's probably the last two factors is the most important. The tide gauge itself, I wouldn't say. There are nowadays solutions that are probably relatively affordable, but then the maintenance is a big issue, and it is known since many decades. And the number of tide gauges has been decreasing. It's also a political issue. We always have to argue, yes, we have no satellites, but they only track the ocean volume. We really need to know what is happening at the coast. So we need to keep tide gauges. It's hard to tell. I mean, we have to develop a local infrastructure that these measurements are maintained. And I'm not an expert on that, so I can unfortunately, I have to give that question probably to the partners.
So if one looked at the number of tide gauges that are active today, it's now 40% of the peak. Every time one of these is damaged, they're never reconstructed. And the argument is always the same. We have satellites now, why do you need these? But there are a couple of initiatives people are taking to try to get low-cost systems, right? One is to put pressure gauges at the bottom of the ocean near these coastal sites, because that has significant advantages. If you put a pressure gauge, then it's not going to be affected at all by thermal expansion. The same mass is on top of it, it's just distributed, and that is seen to be a way of really speeding up the understanding of ice melt, glacier melt. The other is a very state-of-the-art device now that's being developed that actually uses GPS on coastal sites, measuring, so the satellite sends a signal down, it bounces off of the surface and is received by the GPS receiver. So you monitor the coast. In a way, I don't want to get too technical, but that was the sort of noise you tried to get rid of in the old days. You wanted the signal to go straight to the GPS receiver. Now they're doing something quite ingenious. They're looking at the bounce, and they're saying, okay, and if they keep measuring that, they'll get a measure of the change in the sea surface height. And those are now down to about $1,000 each. And so when that technology really takes hold, we might see that everywhere, because it's significantly less expensive than a bottom pressure gauge. So I think in the sea level data community, the engineering community, that's where all the money is going now, to develop these methods. Because then you really will be able to monitor anywhere. It doesn't take $1,000. We have 3 tide gauges, I don't know, Rebecca, 3 or 4 along the Gulf of Guinea. A bit more. So that's $4,000, right? That's doable.
Pressure gauges at the bottom then get affected by the subsistence that you were talking about?
Sure.
Yeah.
Because they'll move
That they
down
will
and
move
down,
themselves.
right? So, but thermal expansion will not affect them. So there are advantages and disadvantages, but the reality is when you see the number of tide gauges, even in the United States, they're not replaced when they're destroyed. This isn't a question of countries in the Pacific, etc. People just don't think they're necessary anymore. Okay. Yeah.
Thank you, Sonke. So a lot of the technicalities that you described are not familiar to me. There are rooms of social scientists here as well, the anthropologists, historians, social scientists. So the technical language itself speaks to an in-group, but also excludes certain groups. So I want to put you in the awkward position that I find myself, right? And trade spaces and say, what does all of this mean when you're talking to people who are not in the language or the terrain that you're talking about? When I'm sure you're going to DC, you're in conversation with some policymakers, people are trying to use this work and ask, what does this mean for us? what kind of questions do you get? What is the takeaway from the non-scientists, the people who are in the policy aspects, who are looking at these findings and asking what is the implication for the wider society, for the climate change? I think that's the kind of, I wanted to pick your brains on what kind of insight that generates. So for the lay person who is just like, I'm not involved in this, but I want to know what does this mean?
Yeah.
You know?
So that's a good point, and it's a very interesting question. And I want to focus now on the U.S. because I'm based in the U.S. and that's where I have most of my conversations. The thing is, the people are still extremely surprised because they still think, many people still think climate change is a hoax. And you have like people like, I call them sometimes the watchers, which tell I lived my whole life in New York and sea level has not been rising. So that is a principal issue that we have, and many people are surprised because what we see along the US, for instance, is we have an increase in what we call high tide flooding, which is actually not the high tide that produces that. It's just the combination of like what was previously, I mean, high water and was handleable 50, 60 years ago, now due to sea level rise leads to temporal flooding. It's not a major extreme event, it's just streets that are flooded, but it hampers our commute. And it actually floods houses in some areas. And people still think we can cope with that, but what people don't understand, that in many places along the US, the costs from these events, when you accumulate them over an entire year, they equal a major hurricane making landfall in that region. So it's already a very costly thing. I'm living in New Orleans. I can tell you what it means for me. I'm paying $7,000 a year for my insurance for the house, which is not handleable for a normal person. I was visiting my friend in Orlando due to the landfalling hurricanes. His hurricane insurance went up from 1.5 to 6,000 within a matter of like a couple of days. So that is what it means, and people have to relocate. We see that in southern Louisiana. We have already people who need to relocate, who are already in the process of relocating. We lose land. Like south of New Orleans, we have been losing land like on average since the 1930s. We have been losing land every hour in the size of a full football field. Every hour. So the full amount is as large as the entire state of Delaware. So that is what it actually means. Like we are already in the middle of it, and many people are still not realizing it, and they keep blaming politicians, for instance, for the increased costs. But it's a natural thing, like with insurances, for instance. It is already a sign of sea level rise and climate change that leads to this.
So there seems to be a challenge between, what you're finding, but also the reception in
Yes.
terms of the people as well, which is why we have conferences like this.
Thank you, Sonke, for that wonderful presentation. But I'm looking at the architectural investments that this kind of phenomenon will affect. So it means that strictly you might not be able to develop a very sustainable architectural solution in terms of adaptation to this region. So what would you suggest? Is it the reducing of the anthropogenic activities along these areas, or also balancing it with the natural one to be able to come up with an architectural framework that will be sustainable in those coastal areas? So I want to have your view on that.
Yeah.
Thank you.
So an important factor here is to realize that sea level rise is a very slow process. And we are already committed with the greenhouse gas emissions that we already put into the atmosphere. We are already committed to a multi-centennial sea level rise. So even if we would stop emitting greenhouse gases right now, sea level would still rise. But if we stop emitting greenhouse gases, we can slow it and we can keep it to a level that is hopefully manageable for many places. So, but again, like we want to avoid the unmanageable, but we are already committed to sea level rise, which means that we need to adapt. So we need a combination. We need political efforts in reducing greenhouse gas emissions, which and then at the same time we need to develop locally adaptation measures to cope with the impacts of sea level rise.
It will be interesting to see how these return periods might vary on the Gulf of Guinea, how you will project this to continue in this area, because when we talk about a vulnerability index, that's going to be, putting aside the issue you made, which is a very good one, that this day-to-day annoyance of flooding can add up to significant cost. I think that return period, that reduction in the return period is really going to be underpinning all of our vulnerability ideas. Like, where is this all going to go, and does it vary along the Gulf of Guinea would be important.
Yeah.
Benji, another question?
No. Well, that's what I'm wondering if this is a little bit tight now. But because they try to get data from the Navy, they have. They're not willing to release it. As far as Nigeria is concerned. And the other group that have to do with as a cabotage law, people in the ports. So for the public, and you are thinking and you get a public job, so you are dependent on looking at tidal, I mean the daily tidal movement. But it doesn't suffice. So that's the worry. If the military refuses to release their information, if the people in the port, via cabotage law, which is an international law that the ship have, they are not willing to release the thing. And here you are, you have to think about what will happen tomorrow. I don't know how we can do that fast. Every time we get this simulation coming in, I'm just kind of wondering. It is.
I mean, I probably don't have an answer to that, but it's interesting because I'm traveling to Washington to the Department of Defense because the military should be worried the most because they don't want to have their daily operations impacted, yes, interrupted. So that's why we actually, for the U.S. Department of Defense, we now apply all this stuff to any military installation worldwide. So they are very well aware. So, but I would guess that requires a political lever to actually make sure, because it should be public data. Right?
Just a couple of brief comments. Tunji's comment underscores for me the importance that some of these conversations I think we should have in West Africa and have some of our government people present so that port authorities, people in the Navy, they can see the difference their data can make to this kind of market, for them to appreciate the questions that she asked, that some of these tide gauges are actually not very expensive yet. It might be maintenance. I think a better understanding of how the pieces come together would help. And maybe we should be thinking about how we have some of these conversations in West Africa with some of these government bodies present, because they are not, I mean, NUMA, the National Institute of Marine and Oceanographic Research, they are scientists there. A friend made a comment about the Cocoa Research Institute in Ghana. that they have more PhDs per square meter than any place in Ghana. So it's not like they're not scientists. So I think we need to find a way to have these conversations, not in isolated pockets, but talking to each other. But my question is this: as you were talking about anthropogenic forces, you made a comment that caught my ear about the threat or the fear of litigation, as we have a deeper understanding of, I guess, the human role. And I think to us in Africa, where maybe changes in our lifestyle may not be that impactful in terms of reducing greenhouse emissions, but we cannot just say, we didn't do it, they jacked us up. So what can we do in our part of the world in terms of how we live our lives to at least help moderate some of these things that we are seeing? I mean, my colleagues tell me, no, we shouldn't put our eyes on loss and damage. No big money is coming. My economist friends tell me that. What can we do at our ends? Or is this beyond us?
I think the most important part is, again, I would answer, the most important part is to adapt and to realize that we have had many generations before us who were way more flexible in terms of adaptation. So we have become very stationary as a society with all the progress that we made. But then on the other hand, of course, I'm not an expert on climate litigations. I know that a lot of stuff is going on, and that's what part of my motivation is, to actually provide a product that allows these kind of comparisons. But I think it should be assessed in more detail what that really means, and then to have actual numbers at hand to hopefully drive change, at least for the future. Yeah.
But certainly, the COP, for the first time, developing nations, if I can use that term, you correct me if that, have used this. I mean, when the United States, for example, agreed to a sort of $30 billion thing, it's a drop in the bucket compared to what these projections or these analyses show is the problem. I mean, West African countries can argue now, here's how much we have faced because of what you have done. And I think it opens itself up to much more realistic threats of lawsuits, etc. And I think largely in the next 5 countries, you're going to see these numbers rise astronomically, because there's a much deeper understanding now of how in one part of the world we're affected by emissions globally. And I think you see this in the COP meetings. Every year we're getting closer and closer to more realistic assessment of how much climate change and sea level rise produced by emission rate has affected specific areas of the world. And so suddenly projections like the kinds you show are being shown at these COP meetings. That wasn't true 5 years ago. So I think a much more realistic assessment of damages to Ghana, Cote d'Ivoire, and Nigeria is at our fingertips.
Yeah.
Other questions? So we should break.
Yeah, I think we've gone beyond a sign of how